All right, how's everybody doing tonight? Welcome to my channel. This is an educational channel, and we focus on theories of everything, all-encompassing theories, magnum opuses of people that you've never heard of before, the esoteric and the obscure, and the very useful, but that you probably haven't heard of it. Because there are certain people out there that like to maintain the status quo, and they don't want to bend from their paradigm or admit that they overlooked something or that they commit to actually learning something new. And so they barricade the doors and don't let new research enter into their sphere. And so we're trying to shed some light on that. Today is the 347th video that we've done on Dewey B. Larson's reciprocal system of theory. Mr. Larson put out his theory in the 20th century, had his first inklings way back around 1930, and finally put out his two fundamental postulates in the late 1950s, and then took his two fundamental postulates and wrote up his basically took his postulates and went through a period of deduction where he said, well, okay, if these are my postulates, then this is what is the result of my postulates. And I went through those in a number of videos earlier called The Outline of the Deductive Development of the Reciprocal System. So you can go back and take a look at those. But basically, he deduced a theoretical universe, and then he compared his universe to the universe that the mainstream scientists had come up with through their observations and measurements. And it was a lot of interesting work came out of that. In general, Larson's universe was almost identical to the Newtonian universe, except in those areas that were what you would call so-called relativistic areas, where Einstein had to make revisions of the Newtonian universe. Those are the same areas that Larson's theoretical universe also adjusted. But Larson's revision of Newton, I think, is much more sound. He's using a fundamental theory and not just picking and choosing and using somebody else's mathematics, and it's conceptually sound. Larson tells you why he's veering off from Newton, and then he shows you why. You know, it's not just, oh, here's the new math, here's the different way of doing it, but he's actually explaining why he's coming up with these different things. So I think it's very useful. Now, Larson died in 1990, and he left behind many books and articles and his postulates. And since then, there have been a small group of people who have attempted to push the theory forward into new areas and to solidify it and to teach it. And two of the main people involved in this are Dr. Bruce Peret and Dr. KVK Nehru, and they came up with what you call RS2, and that is the re-evaluation of the reciprocal system. What I feel was needed revisions. Larson admitted that he could have made some mistakes in his derivations, even though he believed that the fundamental theory is correct. Whether it was applied correctly in all cases was another matter. And so Peret and Nehru have done some great work in revising things where needed. And one particular revision that we've gone over is with the fundamental postulates. And I've basically, in my summaries here of all of these videos, I've kind of gone with Larson's postulates when I tried to explain the theory. But now that we've covered the RS2 postulates and kind of shown that they are a little bit more encompassing and inclusive, I think we're going to try to stick with these RS2 fundamental postulates, at least explaining this going forward. So to get the basic gist of the reciprocal system, basically Larson is saying that the universe is not made out of matter. The universe is not made out of energy. It's not consisting of a unified field of forces, but the universe is made out of motion. And for Larson, other people have arrived at that conclusion in the past, luminaries such as Descartes and Thomas Hobbes. But Larson made his more distinctive because he defined motion as the relationship between space and time. And so there are some caveats to that, and those are kind of in the fundamental postulates. Now, these are the RS2 fundamental postulates. The universe is composed of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is the universe conforms to the relations of ordinary mathematics. Its primary magnitudes are absolute, and its geometry is projective. So those are the 2 fundamental postulates. That is the basis of all of the reciprocal system. And it is deduced. You can deduce a whole theoretical universe from this. Now, I'm not exactly sure here. If I were revising this postulates, I would maybe add one more word, which would be scalar motion. The universe is composed of one component, scalar motion, because there's kind of a fundamental difference between motion as we normally think of it and scalar motion, which is a kind of a fringe, thought of as being kind of a fringe, anomalous kind of motion. A scalar motion is a motion that has a magnitude, just like your normal motion. Think of velocity. The car is going 20 miles an hour due east. 20 miles of space in 1 hour of time in the direction due east. But a scalar is something that has only magnitude. It has no units attached to it, no directions attached to it. And Larson builds his universe out of the scalar motion, not out of vectorial motion or velocity. So I would maybe also add that concept of a scalar motion. The universe is composed of one component, scalar motion, and I'm not exactly sure why Peret doesn't include that, but I bet you he has a good reason, and I'll probably figure it out at some point. But so those are the three main things about the motion here. The universe is composed of one component, motion, scalar motion. Now, scalar motion, what is Larson would call that clock time and clock space. Clock time, the time is always getting later and later and later and later, but in no specific direction. And so we understand that concept of the clock. The clock is always getting later and later and later. But clock space is the universe is getting farther and farther and farther apart, but in no specific direction. And you can envision this using a balloon with dots on it. You blow up the balloon, all the dots are moving away from each other, but in no specific direction. This is a scalar outward motion. And this was also observed, that all of the distant galaxies are moving away from each other. Okay, so there is no specific direction, but just a motion away from each other. So that's clock time and clock space. That really is encompassing scalar motion. And then you have coordinate time and coordinate space. That is the three-dimensionality of it. X, Y, Z coordinates. We generally think of space in that way, but not so much time in that way. But time also has three dimensions. Time and space are reciprocals of one another. So by definition, they have the same properties. So what quality adheres to one is also going to adhere to the other. So we know generally that the clock is always getting later and later, and so we have to attribute space having that same quality. And we know space to be three-dimensional, so we also attribute that to time, coordinate time. And then the discrete unit postulate, both space and time come only in discrete units. You have to have a full unit of space and in order to have space, and you have to have a full unit of time in order to have time. So if you don't have a full unit, then you don't have anything. And if you have exactly 1 unit of space in 1 unit of time, space over time being speed, 1 unit of space over 1 unit of time is the speed of light. Larson refers to that as unit speed. So unit speed for Larson's system is basically the background. This is what's always existing, which makes sense in a universe of motion. In a universe of motion, you expect motion to be the primary thing and the first thing, that is there, the thing that's always there. So you have the speed of light. Now, this goes against what Einstein is saying, where Einstein is saying that the speed of light is the maximum speed of the universe. In Larson's system, the speed of light is the midpoint of the universe, the null point, the 0 point, the origin, the reference point, the ether of this universe, and that there is an entire half of the universe that's moving faster than the speed of light, which Larson refers to as the cosmic sector, along with the half of the universe that's moving slower than the speed of light, which Larson calls the material sector. This is the half that Einstein knows about. Now, fortunately, the cosmic sector and the material sector are generally reciprocals of one another. And so all you have to do to understand what's going on in the cosmic sector is to understand what is going on in the material sector and then invert the roles of space and time. So, for example, in the material sector, you have relationships based on coordinate space, 3 dimensions of space, and clock time. The clock is always getting later and later. But when you cross that speed of light boundary and move into the cosmic sector, you have coordinate time, 3 dimensions of time, and clock space. The clock is always getting later and later and later. So that's just a general idea how it works. Okay, now we're looking at actually an article here that was written by Bruce Peret, Dr. Peret, and he has a series of about 9 articles that are RS2-101, RS2-102, RS2-103, etc. This is RS2-104, and it is it is titled Scalar Motion. So we're going to learn a little bit about scalar motion. Now, we started this article last time, so if you want to hear the beginning of this, you want to watch yesterday's video. But today we're going to take over. Larson just got done talking about what a scalar is, something that has a magnitude but no units attached to it, no direction, no no any kind of units, pounds or distance, anything like that. A scalar is just the magnitude. And then there's also scalar orientation, where you're using 2 different numbers, a ratio, basically greater than, equal to, or less than is the scalar orientation. So if you're putting one over the other, you have less than 1, 1, or greater than 1. Okay, now getting into the rest of this article. Recall that the minimum scalar magnitude is unity, and it is a finite quantity. So the ratios of A over B or B over A will never become undefined, because neither A nor B can be 0 or infinity. So when the scalar orientation can never be 0 or infinity. Note that in the low and high orientations, the possible combinations of scalar ratios are unlimited. But where A equals B, only one ratio is possible, unity. The scalar orientation structure therefore shows a natural separation across a common scalar boundary of unity, which can be used as a reference point, or as Larson calls it, a natural datum. This gives a place or a location in which we can begin to define scalar motion. But it has a problem. So this is what I was just referring to as the speed of light. The speed of light is where A equals B, and you have a scalar orientation of A equals B equals 1. Unit speed. But it has a problem. Given any ratio, there is no way to determine if you are observing A over B or B over A. Another reference point is needed to determine the orientation of the ratio itself with respect to an observer or environment. Sorry, I'm going pretty slow on this because that's a point that I've never picked up before, and I'm just trying to soak it in myself. These videos to a certain extent are kind of selfish, because I might be the person who learns the most from them, because I'm always kind of picking up new stuff. I'm always covering stuff that I've looked at before, but, you know, I'm learning this, you know, just like everybody else out there. I've just got, you know, maybe a little bit more experience at it. But now I'm kind of understanding where he's coming from with that. I'm not sure where he's going with it, but at least I understand where he's coming from. Okay, this can be found in the invariant property of the cross ratio. So when we have that unit speed, we still don't know whether we are observing A over B or B over A. And in order to do that, we need another reference point. So he's bringing in a second reference point. Okay. Now this section is called invariant. And apparently the definition, a quantity or expression that is constant throughout a certain range of conditions. And he says a cross ratio is literally a ratio of ratios and is the only projective invariant to all strata of geometry. Okay, now I think he's talked about this already, the different strata of geometry. Euclidean geometry is basically like the lowest strata, and then there is metric geometry, and then affine geometry, and then projective geometry. This projective is the most inclusive geometry, and it cascades down as you become more and more particular, or as there are more and more constraints. And he's saying that the cross ratio, which is a ratio of ratios, he says it's needed to determine the orientation of the ratio itself. You can find it in the cross ratio, the other reference point that's needed. So a cross ratio is literally a ratio of ratios, and it is the only projective invariant in all strata of of geometry. In a scalar sense, it relates two scalar orientations through a ratio, and that ratio remains constant. Okay. Lost again, but not too far lost. Hopefully trying to redeem myself here. Giving a secondary orientation to the ratio and producing scalar motion, one can also think of it as the ratio of slopes between two lines on a graph. There are now two things to consider as the basis of scalar motion: the cross ratio and the scalar orientation. The cross ratio introduces the concept of association. In a geometric sense, it is like 2 points joining to form a line, except here you join two ratios to form the cross ratio. Now, I'm still not understanding what the second ratio is. He said you needed a second reference point, but does that entail that there's a ratio there? The result is a concept we call dimension. Okay, so the result of 2 points joining to form a line. The cross ratio introduces the concept of association. In a geometric sense, it is like 2 points joining to form a line, except here you have two ratios joining to form a cross ratio. Okay, now he's here to define dimension. This is kind of, I'm sorry I'm going so slow. Maybe you guys are getting this a lot better than I am, but I'm still a little bit confused. Okay, dimension. The definition of dimension is a magnitude that independently or in conjunction with other such magnitudes serves to define the location of an element within a given set. Well, that definition doesn't do much for me personally, but a magnitude that independently or in conjunction with other such magnitudes serves to define the location of an element within a given set. A scalar dimension is a cross ratio where one scalar orientation is fixed at unity, the natural datum, which I would say is the unit speed or the speed of light, and the other varies in order to make a relative measurement to the natural datum of unity. So the other scalar orientation is, it varies in order to make a relative measurement to the natural datum of unity. Scalar motion is another term that is often used with very little understanding of its meaning. Scalar has already been defined, so let us examine the term motion and its connection to the concept of a scalar. Okay, we're going to get into this tomorrow. I was hoping we were going to finish this video, finish this article in this video, but we're going to have to extend to tomorrow. Just kind of going slow over this. This is very fundamental and important stuff, so I'm just trying to go over it very slowly. Again, possibly selfishly, because I'm trying to get it, but I feel like if I can get it, then I can help all y'all out there, you know, get it too. So I'm looking for that eureka moment that just hasn't quite clicked into place with this article. And that's happened with me with Bruce's work before. You know, I get it eventually, but it might take a while. Is what it seems to be. He writes very much unlike Larson. Larson kind of like every detail he puts in there, and he gets like verbose, where he's like, you know, stating everything, and it's just like he makes sure that you've got every step of it. I don't even know if that's true. He seems to write that way in many cases, but then sometimes he kind of pulls something out of his hat too. Peret, he seems to skip a lot of steps sometimes, where I think he just assumes that you know certain things. I guess Larson does that too. So, you know, I guess the lesson here is that there's a big difference between, you know, really knowing your stuff and being able to teach it. So I guess sometimes maybe it takes somebody who doesn't know their stuff that well to be able to teach it so that they can empathize with the person who's trying to learn it. Okay, we're going to leave it right there and resume this article tomorrow. Thanks for tuning in tonight, and have